here again with another upcoming presentation from Edwige Ravry. She is from Total Energies AM and Digital Warehouse product owner. She will be speaking to us about how AM is disturbing the energy industry. Before handing up the floor to her, I would like to say a few words about her. So after graduating from HEC Paris with the MBA, she joins Total Energies in the 2070s as an economist, working first in Paris, then Aberdeen, Scotland. From the very start, she found herself drawn to technical topics, and during her following assignment in Canada, she transitioned from GV representative to development studies lead. She then went back to school to become a drilling engineer and went on a rotational assignment, working on a driller rigs in Argentina, then Scotland. Following an equipment failure in January 2017 that caused significant delay to operation, she Googled additive manufacturing and had an epiphany. One day, oil and gas operator will store spare part as virtual files in a digital warehouse and print them on demand, close to site. She embarked on a quest to make this vision come true and has been at it ever since. Edwige's current role in additive manufacturing and digital warehouse product owner. So thank you for joining us today and giving time to share your insight on how AM is disturbing the energy industry. You may share your screen, please.
Thank you so much, and I apologize. That introduction was a mouthful. I'll make it shorter next time for sure.
No problem.
Can you see my slides?
Yes, I can see your slides. If you can just say masque.
Yes.
Yeah.
There we go.
Okay, the floor is yours. We're looking to hear. Please ask your question on the chat box or the Q&A, and then feel free to upvote the most question that you want to ask the presenter at the end of the session. Thank you, everyone. The floor is yours.
Thank you so much, Malika. It's really exciting to be here. Fantastic event. And I have to say, I'm used to presenting my work on 3D printing to an all-energy audience, people who also work in oil and gas and the energy industry. So this is kind of a first for me, trying to bring it to a wider audience. So a very exciting challenge. And the story I'm going to tell you, which is how additive is disrupting the energy industry, really started here on this picture, where you see an oil and gas production platform. So these can be onshore, but quite often they're out in the middle of the ocean. And if the water is very deep, then they will look like a boat, which floats on the surface. And you reach these platforms via helicopter, and then you stay for a number of weeks, often 4 weeks, and you work 12 hours per day for those weeks, and then you go back home and you have roughly the same time off. So it's a rather unusual lifestyle, a very exciting one. And one day, when I was there drilling a well, we had a failure. This piece of equipment that you see here, which is called the Smart Tracker, is a big robot that goes and grabs 30 meters of pipe to make a connection so that you can continue to drill your well. And this simple coupling that you see here had broken. It's not something that normally breaks. We did not have it in stock. It broke on a Saturday, and by the time we got a replacement, it was Tuesday. So no matter how much effort we made to try and make use of that time, we did end up with a full day lost. And at that time, that cost about 400,000 euros. And that led me to Google 3D printing. Again, January 7, 2017, I Google it and I realize that there's already been, for instance, turbine blades printed that rotated at 10,000 rotations per minute and operated at 1,000 degrees Celsius. So way more than you would ever see in a well. And that was my epiphany moment. And so after a lot of pitching and sharing this passion, I was able to convince Total's R&D department to create a full-time position on additive. And my task was to try and list all the possible use cases for this technology for all Total's businesses, and any material from polymer to extruded concrete, metal, ceramics, any size and any level of maturity. So it was a huge, super exciting task. Fast forward, now this journey has moved from research and development into the digital organization of Total. And I'll talk a bit more about that in a moment, because Total Energies as a company is on a super exciting journey. What I've showed you so far is the old school days of drilling for oil and gas, and we're resolutely moving away from that and into a super exciting future. So this is a corporate slide that really reflects Total Energies' new ambition, which is to be a major player in the energy transition. Total Energies is committed to providing affordable, clean, reliable, and accessible energy. And we want to increase our energy production while reducing the emissions associated with this energy production. And it's that challenge that we must meet with our customers, stakeholders, and society as a whole in order to address the issue of climate change. And we promote renewable, decarbonized energies. We produce and make fuels, natural gas, and electricity. So that kind of gives you the overall view of what the company does. And in particular, we're investing massively in solar and wind to become one of the top producers of renewable energy, top 5 producers by 2030. Below here, you can see all the energies that we now focus on. You can see that it's a lot broader than what it used to be. And a lot of effort is being put on the newer energies to the right. And I'll show you how AM are contributing to those as well. Now, 4 main pillars in this strategy, focusing on natural gas, biogas, and hydrogen, becoming a world leader in electricity, decarbonizing, which really means reducing the emissions related to the oil and gas that we will continue to produce, and going as far as developing carbon sinks, so investing in ecosystems that can naturally sequester the carbon. So this is all very exciting. And of course, in order to deliver this ambition, Total Energies has also decided to invest heavily in digital. I didn't want to have too many corporate slides, but imagine this. There's an entity called the Total Digital Factory in Paris headquarters, where 300 people are working full-time on developing the digital solutions we need to reach these ambitious goals of ours. And it's in that context that I've been asked to continue working on 3D printing, and in particular on digital inventory, which I'll come to in a moment. So what's the business case we see for additive? Well, we took the first few baby steps in 2018, and even before, actually. You could say it's been 10 years since we started down the road of additive. And what became clear very quickly is that you sometimes have the opportunity to make a relatively simple component, non-critical component, and if it addresses a critical shortage in the field, it can save you significant cost. So these 2 examples up top here from 2018 both saved us hundreds of thousands of dollars. And this component on the left, for instance, was designed, printed, and shipped to Nigeria in 10 business days. So this really opened up our eyes to how quick additive manufacturing can be. And so then if you can reduce your lead time, for instance, it used to take 20 weeks to cast an impeller, but if we can now print it in 2 weeks, then why would we need to store it on the shelf? Could we not imagine encouraging our supply chain to give us virtual spare parts that we would print on demand? So that's what we mean by the digital warehouse, the digital inventory. Now, of course, so far we've spoken ISO design. You're not changing the shape drastically, or that's not your main goal. It's all about reducing lead time and inventory. But of course, we're also interested in going much further with AM to improve the efficiency of our equipment, reduce their footprint. And some interesting examples you can see here are valve trims and heat exchangers. So you had a presentation from Hydro just before, and we've been working with them on 3D printed heat exchangers. So this is a very exciting field. And finally, there's a third one, which is not as mainstream, I would say, in the AM community, or not as much talked about, and that's repairs by additive. So the idea of taking a component and adding material onto, for instance, an eroded or damaged zone. So the equipment you see here is a hot expander for a fluid catalytic cracking unit, quite a mouthful, and it was full of erosion holes. And we were able to restore the wall thickness by adding material by laser metal deposition and then machining it back to its original state. If we had had to wait for new equipment, that would have taken 7 months and 7 million euros would have been lost. So it just shows how much opportunity is there. We want to take that technology into the field as well to repair big bulky equipment that cannot easily be dismantled and moved to a repair shop. And of course, these three business case levers all have a very important impact on carbon emissions. So we have set ambitious targets to reduce our carbon emissions, and AM is going to be an important enabler. First, because we will buy less physical spare parts. So we will have less parts that sit on the shelf for years and never end up being used. Some of our sites have up to 50% of their inventory, which is unlikely to be used because it's aging. So that's a lot of wasted raw material and wasted energy input to make those parts. Again, if you make more compact parts or more energy efficient parts, that's also good in terms of carbon footprint. And of course, if you can repair and reuse instead of buying new, that has a huge impact on carbon footprint. So this is really something that we want to pursue in the near future. But one of the main limitations we could see was what are the next parts going to be? And people were often coming to us out of desperation, when they had no other options, and they said, I need this part urgently, I need it in 2 weeks, can you help me? But AM is not fairy dust. And quite often we had to turn people away saying, it's not a simple plastic component, it's not a non-critical item. So what we mean by that is if something can break without causing injury and or significant production loss, then you can call it non-critical. And quite often the parts we need are critical. So they need to comply to certain quality standards, they need to be tested. And that's where it gets complicated. So we decided to prove that we could overcome that barrier. And that's the next part I'm going to show you. So if you have drilled a well, and then you take your drilling tool up and you run a casing to hold, let's say, the formation, to consolidate it and to make sure that your hydrocarbons are separate from the environment, let's say. So that is a barrier, a protection. And while you're running this down into the hole, you are exposed because this is not directly compatible with the mud pump and the drilling pipes that are on the rig. So we need to have an adapter ready to be used in case something goes wrong, in case we have a loss of well control. And so that's this piece of equipment here. So you can see we're talking a 1.2 meter piece of equipment. And here you will see it printed by wire arc, additive manufacturing, layer by layer. And here you see it after machining, threading. And if it didn't say world's first wire arc water bushing on it, you would have no idea that it was 3D printed. And we were actually unexpectedly able to reduce the weight of this item because normally it's made from a 1-ton forging that is this wide, and you only machine off as little material as you can get away with because machining cost is expensive. It means money. And so you end up with a part that goes from 1 ton to 500 kilos and retains a lot of useless bulk here. But in this case, our partner, Vallourec, suggested we redesign the part and go to the smaller size much earlier in the manufacturing process. Hence, a part that only weighed 350 kilos at the end of the wire arc build. And after machining, we were down to 250 kilos. So you see a saving of 50% comparing to the conventional part, and much less waste in raw material. And this also translated into a CO2 footprint reduction of 50%. Here you see the part pressure tested. And here you see it field deployed in February 2021 in Scotland on the same site that you saw in the first picture. So the circle was complete to some extent. My dream from 2017 had finally become reality. Now, because everything went well in this drilling operation and the well was in control, we did not need to use it. So it went back into the warehouse and it will come out again next time we drill a well. And of course, this was challenging in the sense that we had to make 2 components as per the DNVGL guideline, which is now a standard and which Valeria also mentioned in her presentation just before. And so making 2 components and destroy one to prove that the other is fit for purpose, of course, costs money. So that's the challenge we have, and we have to be smart about this. It also takes time, so we need to decide ahead of time which components we need, and if possible, work with others to share the cost. Here is an example of our second safety critical component, which we have, well, it's almost field deployed, so close. It took about 2 months to print, and to test in Scotland with Technip FMC. And then the component was shipped to Congo, which took a while. Hence, again, that dream that many of us have of actually having in-country 3D printing capabilities in some of these places. And I'll get to that in a second. And the final testing, pressure testing, and coating has been done. So now we're really just waiting for this to be installed on a Christmas tree in the field. So this, just like the previous component, is a temporary component. It's at surface. It's easy to inspect. So we're still some way off from being able to put components in a well, quite a distance below surface. But they're still very exciting breakthroughs, and it shows that you can have a component quickly, even if it is critical, like these two components are. Now, the next subject that I'm going to talk about is the digital warehouse, because this is what my current focus in my role is today. And so it's this idea that it's great to have some parts, but if we want to scale the number of AM parts being used, there's something missing. And that's the digital thread to achieve a vision. This vision I mentioned in the beginning of our suppliers making spare parts available to 3D printing facilities across the globe, so that we as an end user can click, place an order, and receive the part with as short a lead time as possible. We cannot convince our maintenance engineers to stop putting parts on the shelf if we don't have a firm belief and good assurance that that short time will materialize. And if we wait for each of our original equipment manufacturers to invest in their own hardware and print in-house every part they make, it's going to take 15 years. And we cannot afford that. We need to speed up that transition. So it's really important to go from a linear supply chain to a circular supply chain, where the company that comes up with intellectual property, with the design, can rely on others if needed to print it in order to have some supply chain flexibility. So in order to make this vision come true, we've partnered with Equinor, Fieldmate, and Siemens, who had already together built a first version of a digital interface. So we are currently in the process of testing that together. And this product, which will be launched commercially in Q2 2022 and made available to many more end users and manufacturers, aims to address the challenges listed here. How do you select the right parts? As an end user, we have many. We don't have a lot of technical information about them. So how do we do that? How do we digitize them? They are not, let's say, designed for additive today. So how do we overcome that backlog of old parts, even if the future may be designing directly for additive? How do we qualify the parts? As you've seen, it is possible, but there's still some roadblocks ahead. How do we share the value between the company that designed the part and the company that prints it? How do we generate trust in that circular supply chain? How do we secure that IP, track the transactions, and manage the payment? And how do we integrate this solution with our existing tools? We have ERPs for procurement and many other systems. And if we design something new without taking that into account, we will fail. So we are addressing all of this as a team. It's a super exciting journey. And we are kicking off, as we speak, some pilots with a few OEMs to make sure that our product also fits their needs. And the categories of equipment that we have already identified as suitable within the short term for this digital interface are valves, rotating equipment, and drilling and subsea. So a few more words before the Q&A, just to give you a flavor of what the future looks like. So we are exploring at the moment some very exciting topics. So all these pictures here are widely available on the web. I cannot show you necessarily what Total is working on, but it's just to give you an idea and share some of the exciting success stories out there. So here, for instance, you see MX3D making structural demonstrators, so a bridge, architectural elements, and they've also made a pipeline repair clamp. It's very exciting. It shows the potential, and we want to explore that and to see if we go back to that first picture you saw of this big structure in the middle of the ocean, lots of steel. What can we do to make that leaner, to make it lighter? If we redesign it, we imagine there's huge potential to make it lighter. And Hydro have also shown some very interesting examples with hydraulic manifolds. So that's also an area where we know that there's so much to be done. And again, I think like many other end users, it felt easier to think ISO design and we're just replacing a spare part. But we know now, we've really embraced the fact that we need to go to full redesign together with our OEMs to reap the real benefit of additive. And so that will one day apply to our Christmas trees. So what is that? It's essentially, it's some valves on the seabed. And they're expensive, extremely long lead times. And today, their engineering, the way they're built, is driven by the fact that you need to build the body, but then access it internally to, for example, clad it with a different material, to add features. And what we would like is to be able to make these layer by layer, maybe with several materials on our printers. We're thinking wire arc for this, but who knows? And yeah, to redesign them completely for AM, make them lighter, make more compact. We think that is something that is in our future, and we're very excited to embrace that challenge. Here are some other very exciting examples, and now I'm starting to steer towards the future of Total. We're very focused on our own energy consumption and how to reduce our emissions. So we were very excited when Eureka Pumps shared this example where a single impeller in a pump can be redesigned to reduce the flow passages. And even if your production has gone down by more than 70%, you could still reuse that same pump. You don't need to buy a new pump. You just change one component. And this component has been printed hollow, which would have been impossible with conventional casting. And thanks to this simple one component swap out, they eliminated all the noise the pump was making, and the end user had an electricity consumption that was reduced by 70%. So it's a fantastic success story. And similarly, you'll be able to find on the web information by John Zink and Desktop Metal on this LNG burner that they've manufactured, which saves considerable funds for LNG tankers every year, thanks to a better fuel-air mixture, which is, again, a super exciting example of what design for additive can unlock and how it can help us reduce our carbon footprint. And I think this is going to be my final slide today. And so bear with me here, because there's a lot here. I've talked about the fact that Total plans to produce hydrogen, capture carbon, and go into renewables. Well, we're finding out that additive is going to be a key enabler to build the prototypes that we need as we learn about these new activities, but even to make the final shape of the actual equipment that will be doing these all-important tasks for us. I'm again going to show the hydro heat exchanger as an example, just so you see, because the first theme is about complex small shapes. So you see the example here of this gyroid heat exchanger. Well, this is applicable, or something similar, let's say, to carbon capture, for example. Okay, again, this is an image you can see on the web, but a company that Total partners with, Svante in Canada, and their system, as many other carbon capture systems, have some complex shapes to them with small passages and where even the surface roughness can be important. So there is a million opportunities there to optimize that so that we can capture more carbon and make that process less expensive, and so that it can be scaled up. And same thing if you're looking to produce hydrogen, or to combine hydrogen and CO2 to make other products, for example, which is something that Total is investing a lot of research funds into and has had some really exciting breakthroughs recently. And yeah, here again, 3D printing was a key enabler. And now on a completely different end of the spectrum, we have wind power, where there's been very exciting information provided by GE and Holcim, which you can also go and see for yourself. And they've shown that for an onshore wind turbine, you can 3D print the body with concrete, therefore making it bigger than what you could ever transport by road. Because if it's too big, then you need to, take the street lights down. It's extremely expensive to transport a really big piece of equipment. Well, if you 3D print it in situ layer by layer, you can make it much bigger, therefore much taller. You can reach areas where the wind is stronger, and you can improve, let's say, the efficiency of your wind turbine by 30%. So again, we can see a very exciting future there, which Total will explore as we get into the offshore wind market. And so that's it for me today. Really happy to take some questions.
Okay, thank you, Edwish. I hope I'm pronouncing it well this time, for the presentation and explaining the benefits of additive manufacturing and highlighting, make to order versus make it to stock, and for reliable supply chain for AM metal and, polymer production to reduce cost and logistics. And then as well, you highlighted very well how it would be beneficial for our planet to reduce the carbon footprint. I would like to take a few questions here with us. How are you dealing with the impact of corrosion? In my experience, 3D printed pump part corrodes significantly faster.
Wow. Well, Mr. or Miss Anonymous, if you'd like to contact me after this presentation, I'd be very interested in hearing more. The impellers that we field deployed have been in service for a number of years. They've been made from Inconel 718, and they've performed well so far in service. So I think it depends a lot which service we're talking about and which material. But yes, we are monitoring these parts to gain more experience, and would love to know more from others who have relevant experience on this topic, because yes, aging of materials and corrosion is a challenge. So generally we tend to, let's say, step up a bit in terms of the, let's say the material. We go for a more highly alloyed material, etc., to mitigate those issues.
Thank you for that. And then we have a question saying, seeing that your digital library is from a third party, how then do you deal with the repairs? Do you have the right to repair?
So one thing that I didn't explicitly say maybe is that we do not intend to become an OEM or a repair company. We will still be working with our supply chain, and what we're really doing is we're trying to encourage our supply chain to embrace additive. So we work with a number of companies for repair, and we hope that they will, let's say, embrace the technology. Of course, still we can face the issue of obsolescence. We have a piece of equipment, we don't have the drawings, the OEM no longer exists, and that there are challenges around those situations there, but there's usually ways around them as well.
Okay, wonderful. What part of the AM life cycle / supply chain in Total Energy is involved in, and do you have AM machines?
Okay, so we have, actually, that's something I forgot to mention in my presentation, is that our Angolan affiliate have just made the decision to purchase Total's first metal AM system. So that's very exciting. Stay tuned for more news on that. But other than that, I would say if we're for our affiliates that are in the Americas and in Europe, there's such a capable supply chain already there that it does not really make sense for us to acquire our own printers. We will only do so in remote locations. And which part of the AM life cycle are we involved in? I would say many different aspects of it, both research, purchasing components, in embedding AM into our procurement, in our supply chain as it is today. And then, yes, it will also be repairs of AM components down the line and so on.
Okay, wonderful. Just to follow up on that question about your Angolan partner, what type of AM machines they acquired? What type of process?
I don't know if I can say too much about it, but let's say it's a metal AM process which is compatible with an office environment.
Okay, powder bed
fusion. Relatively small size.
Powder bed fusion. Okay, thank you so much for that. And another question: what material are the subsea Christmas tree made of? So
the body is made of low alloy steel called F22. And normally, and then they're cladded internally with Inconel 625.
Okay, I believe that with a wire feedstock.
Yes, absolutely, wire arc additive. Yes.
Yes, and then we have a comment.
Or sorry, they will be. Let's be clear; it's never been done yet.
Okay, yeah, we look forward to it. Because we know that Total was present in the southern African, but then they withdraw because of some disturbance and so forth. So we hope to see you again, guys. Yeah. Bertrand said, great presentation, Edwige. In your view, what is the biggest challenge that need to be overcome to implement a digital warehouse and circular ecosystem?
That's a very good question, Bertrand. There's several challenges, as I listed, but maybe the biggest one is that it can actually be really hard to land a grand vision into something concrete, something that works. And especially when you need several disciplines to work together to do so. You need, people with a contracts background, you need people who know maintenance, and also you need end users and OEMs to sit together, to work together, and to find a common interest, which can be really challenging. Again, we recognize the way the industry works today. If you put a tender out, you want to buy a pump, for example, you buy the pump that you buy the pump that has the most attractive price, and then people make their margins on spare parts for the next 20 years. So if you start saying, I want to buy less spare parts, then how do you still make sure that your OEMs are still no worse off with AM? So that's really, I think, our big challenge. It's the commercial aspects of that. And I'm committed to solving that challenge by April. So wish me luck.
Okay, all the best luck from us and for everyone. Thank you again for your presentation and the time to answer the question and everything. It was such a pleasure having you at the industry track, Edwige Ravry. Thank you so much. You can excuse yourself from the stage just by putting your mic and camera off. Thank you.
Thanks, everyone.
Bye-bye.